Hey guys, this is notes number 12. Extremas, change, and bounds. Okay, go ahead and write down the FLT here, and then press play whenever you're ready, all right? Okay, so given a function, you're going to be able to identify three things, okay? So here we have local extremas, change in intervals, and bounds. Okay. All right, here we go. You can hear my kids in the background. Okay, so pretty easy to identify what a local extrema is. Okay, so a local extrema is a general word for maximum or minimum. So in other words, we're looking for a highest and a lowest point. Local just means nearby or in the area. Okay, when you want to go eat local, you're trying to eat somewhere close to where you live, right? And that's basically what it is. So let me draw you a picture here so you can quickly identify it. Let's say you guys had a graph. Okay, and try to draw this as close as possible. Doesn't have to be perfect, but let's say we had something like this. Okay, I'm going to label 3 points here. I'm going to call this A, call this B, and then I'm going to call this C. All right, so here's what it basically is. Local means in the area, okay? Now, this blue graph goes all the way down and all the way up. So there really is no highest or lowest point, okay? But we're looking for something that's local, so in the area. So if you take a look here, what you want to do is you want to imagine if you were to only look in this green square. If you were to only look in this area here, is that red point the highest or the lowest point? Okay, so in this area, okay, A is your local max, okay, because in that area it is the highest point, okay? Same thing here. If you only look in this area, B is definitely your lowest point. So B is your local minimum. All right. Now, remember, even though there are points that are lower than that red point, and there are points that are higher than that red point, the word here is local. So you're only looking inside that area. Now, if you take a look at C, if you were to just look at it locally, okay, we cannot call C a local maximum because slightly above it, there is a higher point. Slightly above it, there are higher points in it. So C is not a local maximum, but also C is not a local minimum because there are points that are lower than it. So here, this is the case where C is neither a local max or min. That's pretty much it. You guys are being able to identify if we have any local extremas. Okay, so for instance, if you think about a linear function, okay, does that line have any local extremas? Pause and press play when you're ready. For any linear function, there is no local max or local min because if you think about any point, okay, there's always going to be something higher than it and lower than it. So for a linear function, positive or negative slope, you tend to not have any extremas, no local extremas. And again, extremas is a general word for max or min. Now, if you think about a right side up parabola, okay, what does it have here? Pause and press play when you're ready, okay? Here, we have a local minimum because that is locally the lowest point, okay? Same thing if you had an upside down parabola, what do we have here? That is a local maximum. So it's just being able for you to identify if we have any local extremas, okay? So let's try one. Here we go. Here's example 1. Find all local extremas. Okay? And let's say I gave you this function here. Y equals x to the 4th plus 3x cubed minus 4x plus a 3. Now, if I gave something like this to you guys, okay, finding local extremas are easy if you have a picture, right? Because you could physically see what's the highest and the lowest point. But now I give you a function, okay? So we have to graph this, all right? You're not going to be expected to sketch this type of function by hand, yet at least, all right? So what we're going to do is we're going to go on the Desmos, okay? If you have a graphing calculator and you know how to use it, by all means, use it. So we're going to type it out. We're going to have y equals x to the 4th plus 3x cubed minus 4x plus 3. Okay, so we have this picture here. Okay, so based on this picture, let me put it a little bit bolder for you guys. Just so you guys don't freak out, there are your axes, okay? Now, based on this here, how many local maximums do you see? Okay. Pause and press play when you're ready, okay? We have one local maximum right here because locally in that area, when we're just focusing on that area, that is the highest point in that area. So what we're going to do is we're going to state that there is a local maximum at negative 0.843, comma 5.08. Okay, so again, there's going to be a local max at negative 0. Oh gosh, I forgot it already. 843, comma 5.08. Okay. Now let's go back to our picture. Did we have any local minimums? Okay, and if so, how many? So here, we actually have 2. Okay, you could have multiple local extremas because of the word local. If you're only looking at a certain area, you could actually have multiple ones. So in this case, there's one at negative 2, comma 3 right here. And there's actually another one right down here. So we're just going to write that down. So at negative 2, comma 3 and where else? 0.593, comma 1.377. We have a local min. So we have 2 local mins and 1 local max. That's basically it. So this is really easy if you have a picture. That's it. So local extremas, we're good to go. Okay, let's talk about change in intervals now, okay? So these are all relatively simple concepts to understand, okay? Change in intervals. My writing is amazing. Change in intervals, okay? So basically, this is what you're talking about, okay? When you're given a graph, you need to describe it in 3 different ways. The graph can either increase, meaning it goes up, okay? The graph can decrease, meaning it can go down, or it can be constant. Constant just means it's not changing in value, so it's horizontal. It's not going up or down. It's just staying sideways, okay? So let me give you a picture here. Here's example 2. Okay. Identify the change in intervals. Go ahead and write that down. Okay. And then I'm going to give you this. Y equals the absolute value of x plus 6. Close it. Plus the absolute value of x minus 4. Close it. Something like this, you are not expected to graph by hand. Okay. Maybe if you had just one absolute value, then you would be able to. So here we're going to resort to, just like how we found local extremas, it's easier if we have a picture. So we're going to go ahead and graph this. So here we go. We have y equals the absolute value of x plus 6, okay, plus the absolute value of x minus 4. Okay. Now, if you don't see a picture, you might have to zoom out a little bit. There we go. So sometimes it's hidden. You kind of have to look around for it, okay? Okay. So if we were to just talk about this graph, right? Kind of like when you guys are reading a book or you're reading a sentence. We read from left to right. Same thing when we're reading our graph. We follow the graph from the left to the right here, okay? So what we're doing is, notice if I zoom out, it's safe to say that this graph, if I follow the graph towards the left, the graph is going to continually go all the way up here. Okay? And same reason, let me zoom in at the right part. And if I follow the graph to the right, it's safe to assume that this graph will always go up and up and up and up. Okay? So this is called end behavior, which we'll get to in another lesson. All right? So we notice, so let's use some words here, okay? When we follow the graph, starting from the left, so let's say starting from, let me see if I can pick a point here. Starting from, let's say somewhere up here towards the left. Now I could start even further to the left, but I'll start here at negative 12.47. If I walk towards the right, is the graph increasing, decreasing, or constant? Okay, is the graph going up, down, or sideways? Okay, so notice the graph is decreasing because the graph is going downwards. It's decreasing up until a certain corner, a certain point. And then right after that point, the graph goes constant because it's just going sideways. It's not going up or down. It's going constant. And then eventually it stops being constant. And at some point it starts to go up, or in other words, it starts to increase. Okay? So look, here's what you guys are going to do. We have to describe it, and you want to use your words very carefully, okay? At some interval, the graph started to decrease. Okay? And then in the middle, it was constant. And then after it was constant, the graph started to increase. Okay? So what we're going to say is we need to include some intervals right here. You guys had practice with some intervals when you guys were dealing with domain. So let's go back. Okay, so we need to describe, well, where was the graph decreasing? Okay, well, remember that I showed you guys that as we walk towards the right, the graph was decreasing, right? Well, it's pretty easy to spot where it stops decreasing because it's right at this corner right here. Okay, now when you're describing an interval, you only use your x values. So at negative 6, okay? So it stops at negative 6, but where exactly does it start? Okay? So does this start at negative 13? Does this start at negative 20? The thing is, we can go further and further to the left, and then we find out that it keeps decreasing if you go all the way to the left. So where is the left, right? How far left can you guys go? So it actually starts at negative infinity, okay? So negative infinity just means far left, okay? All the way up until the negative 6, this is the x value, okay, you guys? You will always use the x value. So from negative infinity to negative 6, the function is decreasing, okay? But then afterwards, starting at negative 6, and all the way to an x value of, it looks like 4, right? Negative 6 to 4, it becomes constant, all right? As far as the open or close goes, when you guys are describing a change in intervals, the intervals will always be open, meaning you will always use parentheses there, okay? So lastly, right after 4, you notice that the graph is going to continue increasing all the way through forever, meaning that you're going to go from 4 all the way to infinity. All right, so when you have a picture, and I'll draw it here, it's not exactly accurate to what you guys saw, but something similar here, just to give you a better idea. This is not to scale, but again, from negative infinity, so from far left all the way up to negative 6, that function was decreasing. Okay, from negative 6 to positive 4, it was remaining constant. And from 4 all the way to infinity, that graph kept on increasing. So this is just a way for you guys to describe the behavior of the graph. Okay, hopefully that was a little straightforward. I'm going to have you guys try one real quick. Here's part B. Go ahead and describe the change in intervals for this function here. Okay, pause and press play when you're ready. Now this one here does require a graph, but you should be able to sketch this by hand because it's a very basic absolute value function. It's a V shape right at the origin, okay? So how would you guys describe this? Okay, so from left to right, looks like it's going down and then it's going up. So using the more technical term, it first starts to decrease and then it increases after. But notice how there's no moment where it's constant, okay? So the question here is, from where to where is it decreasing? So we know from the far left, okay, from negative infinity all the way up to where? Okay, that looks like about 0. So from negative infinity to 0, the function is decreasing. And from 0 all the way on to the far right, the function is increasing. That's it. It's that easy, you guys, okay? I'll give you one more where it's a little bit more tricky in terms of the graph. We'll do this last one here together. F of x equals x squared all over x squared minus 1, okay? A function like this, I don't expect you to sketch by hand, so you would need a graphing calculator or Desmos to graph this, okay? So this one here, I'll go ahead and type it out. Y equals, I'm going to create a fraction right away. Up top, I have an x squared. Down below, altogether, I have x squared minus a 1. And then you got this guy right here, okay? I'm going to go ahead and put in some units for you guys. Actually, if I zoom in, there we go. Okay, with the units, it's a little bit easier to understand. Okay, so remember, we are following this graph from left to right. All right, let me see if I can take a picture of this real quick. Okay, that way I can drag it in here. That's my son right there, you guys. Oh, what an awesome picture. Okay, so this is our picture right here. And I'm doing this so that I can highlight over it so we can follow along, okay? So sometimes it's difficult to know where to start. So remember, we always start at the far left. So if you go all the way to the left, the graph is right here in green. So I'm following the graph. And then take a look at what happens to it, okay? I know at some point it's definitely increasing. Some of you may argue that from -10 to about -4, it looks like it's constant, okay? So let's talk about that real quick. If it's constant, that means that the y values should not be changing, okay? But if you take a look, if I click on a point and I move it, notice how the y values are still changing. So what does that say? Is it really constant? Right? So the y values are slightly changing or slightly getting higher. It's actually increasing, but at a very slow rate. If you notice, if I zoom in enough, there's a slight increase. You notice that it gets a little bit higher each time. So to the naked eye, it looks like it's constant. But if you hold on to a point and you move it, you notice that the y values are actually getting larger, which implies that the function is actually increasing at a very slow pace, but increasing nonetheless, okay? So here, let's write this one out. We know that the function is increasing initially, okay? Then out of nowhere, it pops down over here and it still is going upwards until about that 0. So it increases there as well. But then afterwards, it starts to decrease, go downwards. And then right after 1, the graph appears right up here and starts to go downwards, so decrease again. So we have to describe this, okay? So in this order, it started to increase, then it increased some more, then it decreased, then it decreases some more. So notice how it just went in order here. 1, 2, 3, and 4. Okay, so remember when we're talking about change in intervals, we always start from the far left. So the far left here is negative infinity. Okay, remember the interval represents the x value. So if I stop right there, my x value is -5, okay? Now I'm at -4, -3. It starts to increase, and notice how I get really close to an x value of -1. Okay, so I'm going to stop at -1. Okay, but right after -1, I'm still increasing. So notice right here at -1, I'm still increasing to about 0. Okay, right after 0, it starts to decrease till about 1. Remember, you're only focusing on the x values when you're talking about the intervals, okay? Don't confuse it for y values. But right after 1, the function still decreases even when you go all the way to the right. Another word for all the way to the right is just infinity, okay? Still not that bad if you have a picture, okay? But try it out a couple times. I'll give you some examples for you to try in the homework. But that's pretty much it for the change in intervals, okay? Here's the last easy part. It's called boundedness, all right? Okay, so when we're talking about bounds, it sounds a lot like boundaries, okay? Think about the NBA, right? What are the boundaries in the NBA? So when you're playing basketball, the boundaries is pretty much your court, right? Pretty much every side is a boundary. So this basically means this is as far as you can go before stepping out of bounds, right? So it's the same thing. It's very closely connected to what we learned in the last lesson when we were dealing with range, okay? So for instance, I'm going to give you 4 pictures. So here we go. I gave you a linear function. This function, you would say, is not bounded because it goes all the way up. Remember, that arrow right here implies that that graph will go all the way up, and this graph will go all the way down. So meaning there are no boundaries. It just goes up and down forever. So it's not bounded, okay? Another example of a not bounded function, you'll see later on, maybe a cubic function, where it looks a little bit like that. Notice how it goes all the way up and all the way down, so it's not bounded, right? Here's your second example. Okay. Now, think about your parabola. Okay. This parabola here, notice how the graph goes all the way up. Okay. So there are no boundaries above, but there's actually a low point to how far down it can go. So notice here with this particular graph, it doesn't go all the way down. Okay, the lowest it'll go is that pink highlight right there. So this is what you would describe as bounded below, because there's a boundary below. Okay, there's only so far that you can go down below, but it's not bounded above because the graph goes all the way up. Okay, and here's one more. You might even guess it. So let's try this one a little bit backwards, okay? We're going to try to sketch a function that's bounded above, okay? I want you to sketch any function that's bounded above. Pause and then press play when you're ready. Okay. So some of you might have drawn an upside down parabola. Absolutely, okay? Or you could even do an upside down absolute value function, okay? Notice it goes all the way down, so it's not bounded below, but it's not going all the way up. It actually just stops at that pink highlight right there, or that red highlight in this case. So it's bounded above because there is a boundary to how far it can go up top. All right? So here's the last type. Okay? The last one is called bounded on its domain. That's the technical term. Bounded, just bounded, means that it's bounded above and below. Okay? I want you guys to think about what that really means, okay? If you have a function that's bounded, implying above and below, what kind of function are we looking at? Okay, I want you guys to try to sketch a function that's bounded above and below. Kind of tough to do, but there are functions out there. And press play whenever you're ready. The most popular one, which you'll see this in this course, is the sine function or the cosine function, where it looks like waves. Now notice how I didn't draw arrows at the end, okay? Because actually what's happening to this graph is it's continuously waving and it doesn't stop no matter how far out you guys go. Notice here how there's only a certain high point that it can go and there's only a certain low point that it can go. Okay, so that's basically it. So if I asked you guys for boundedness, you would give me one of these 4. And the easiest thing to do is, if you know what the picture looks like, right, you could definitely describe its boundedness. Okay, so for instance, like this graph here went all the way up and all the way down. So this is not bounded. This graph right here is definitely bounded below because there's only so far that you can go down. This graph here is also bounded below. Okay, hopefully you guys get my drift here. This blue function right here is not bounded. This purple parabola is bounded above. You see enough, then you'll be able to recognize it, okay? So I'm going to have one, and then we're all done. One for you guys to try. Here's an example. I think we're on 3. If it's 4, my bad. Identify the bounds. Okay. Okay. Here's my challenge to you guys. Don't use a graphing calculator. Do not use Desmos. Okay? Answer this question here. Press play whenever you're ready. So, here, this is something that you should be able to sketch by hand. Okay? We know what the shape is going to be because it's squared. That's a bad color because it's squared. And we also know that there's going to be a reflection, okay, as well as a vertical stretch and a horizontal shift of 4 units to the right and a vertical shift of 7 units upwards, okay? So when you do this, okay, I'll do everything prior in purple so that we can keep track. Okay, this is my parent function. I know that I have to reflect it because of that negative. I know that that 3 will make it more narrow, a vertical stretch. So I got something that looks like this. And I know I have to move it 4 units to the right and then up 7 units. So my final product should look like a very narrow upside down parabola that's pushed over 4 units to the right and 7 units up. Okay, I'll get rid of everything else so that it's a little bit cleaner. Whoops. And there you have it. Okay, but let's answer the question. Identify the bounds. Okay, what's the boundedness here? You would just say that this is bounded above. There's only so high that you can go, but notice how the graph goes all the way down. All right? So here, it makes sense because if you think about the range, you guys, okay? The range, it goes all the way down. So all the way down is negative infinity, and it goes all the way up to 7. When it's capped off, you know it's going to be bounded above, all right? So it makes sense with the range, okay? So 3 things. You guys learn local extremas if it's a local max or a min. You learn how to describe if a function is increasing or decreasing using intervals. And you discuss bounds. We have all 3 taken care of. Very simple to do, but definitely practice, okay?